Okay. Hello, can you guys hear me? Can you give me a yes or no in the comments?
Yes, sir.
Yeah, cool. Okay, I'm wondering who and all are there. A lot of familiar faces. Okay. Yep. Uh, okay, and weird backgrounds, as expected. Okay. So the thing is, I'll be covering your 10th standard. Yeah, I hope I remember you, Vivek. Yeah, I remember. So the thing is, there's a private chat as well as a public chat. Now, for most time when you'll be answering something, I'll be expecting you to answer in a private chat. So you can see you can chat with anyone. So there is chat with everyone and many other options. For now, 1 second, I'll just do something else. Wait, I've changed my ID. Um, some of you are giving yes or no's. Okay, cool, cool. Okay. I'll just change my name so that you get an idea of where I am. Okay, that's me. So you have to chat with that account where you see Prajwal there. Okay. Yeah. So it's audible, right? Yeah, cool. Okay. Uh,
Yes, sir.
yeah, cool. Can I get an introduction of who and all are there? So it's just too much wait. Checking out. Okay, okay. Okay, that's a lot. Okay, Navya is here. Okay. Um, okay, cool. So I don't have. Is it possible to answer your questions? Yeah, sure. Nidhi, that would be fine. You can. Some. The Samant Martis. Oh, Samant. Hi. Long time. Lot of disturbances. That's I need to mute it. Okay. I hope now it's fine. Okay. So you can answer with a microphone. Okay. That's not a problem. In fact, you don't even have to use your webcam all the time. For most part, I think webcam is better. Yeah, I do remember Samant. I do remember. Yeah. You were in eighth. Uh, Okay, Shashank says you can't hear anything. I think you've muted your audio. Just check. Please check. Okay, guys, just tell me, give me a yes or no in the this thing if you guys can hear me or not. Just give me a yes or no for now. I just want a clarification. Okay, okay, cool, cool. Missed you too, Samant. Samant, wait. Okay, okay. Shashank has an issue, but I don't know about others. Ratisha says it's not clear. Okay, I'm really sorry. That could be your bandwidth. Okay, your internet might have some issues. There's a very high chance it's your bandwidth. I have muted actually, so I don't think there should be any disturbances. Tanisha, is there any disturbance now? Anvita, is there any disturbance now? Tanisha? Okay, okay, okay. Yeah, you can use the chat. You can use the chat. Okay. So we'll get started. I'll be doing a PowerPoint presentation. So we will be going with the. Oh, before that, how are you guys? How's the quarantine treating you guys? Okay, nice, nice. Okay, bored. Okay, fine, fine, fine. Some are bored, some are excellent. Some are terribly bored. Okay, good, nice. Okay, something. Oh, the Saujanya, yeah, I remember. Farn is there. Okay, Shushruth is there. Oh, Nakshatra is there. Who's bored? Uh, okay, Anaga is there. Okay, cool. Okay, so here's the thing. We'll get started with the presentation. I won't waste a lot of time here because we already lost some time. So here's the thing. I'll be doing optics. We'll be doing optics first. So I think last year you guys studied. I think the laws of what do you say? Reflection, total internal reflection, and a lot of stuff. Wait a second. Wait, Shashank seems to have audio issues. Shashank. Oh, nice, Samant. Okay, okay. What about Shashank? You seem to have some issues. Is it still persistent? Give me a message. Oh, Muralidhar is there. Okay, nice. Okay, Shashank, give me a. Shashank seems to have an issue. You can't hear. Does that problem exist now? Okay, fine. Listen up. We'll get started for now. Okay, I'll just go ahead. I hope there's no disturbance. Okay, with the presentation, where is it? Where is it? Where is it? 1 second. Yeah. So this will become a bit of a recap for some of you, okay, from 9th standard because I taught you optics there also. But it's fine. But it's fine. I think it'll be fine. Not a problem. Okay, so let's get started. One moment. Give me a moment. Participants. Nope. Nope. Rules. You can see the screen. Is it visible? in the chat box? Can you give me a yes or no in the chat box? Ah, the screen is visible. Cool. Okay. So given that you can see this, I can't. So okay, nice. No pun intended. Okay, fine. So we'll go ahead. So first things first, few things. I think I'll start with something we discussed last year. That is, I think you remember rectilinear propagation of light, right? You guys remember that? Yeah. Okay, okay, fine. I'm looking for feedback. Okay, so I think you remember this example. I told you about cats, right? And cats, rectilinear propagation of light. Okay, Nidhi, I was talking about that. So that what do you say? Light travels in straight lines. Yeah, and that cats do some stupid things when they see mirrors. Yeah. So the key takeaway there is that light travels in straight lines, and that's very important. Okay, you've seen cats jump into mirrors. You've seen these scenes last year, but I just want to go on adding layering upon top of that a little bit. Okay. Now here's the thing. I think we discussed this, if you remember last year. You know, all these stupid things about a scene was there. I'll just skip this part because. This is not class 8, this is class 10. I'm sorry. Okay, class 10, Ritu. Yeah. So I think we discussed this, but I hope you remember about light travels in straight lines. That no matter what happens, light always travels in straight lines. And this is very important because, see, how we perceive objects, how do you see something is there? Okay, how do you see something is there? Okay, Vishnu has a question. Do you have a question? Are you experimenting? Somebody has a question? Okay, no. Okay, so there's always this question of how do you see an object? So light travels in a straight line, and then it hits your eyes, and you say that okay, I see the object, so it's there in that location. So that's how usually we perceive objects because we know that the object is there. Now, images in our mind are formed along that line. So when I see an object in front of me, it's because I see that doorknob or anything like that in front of me because the object exists there. The image of the object seems to come from that point. The rays of light come from that point in a straight line. So I perceive that object to be there. Okay. Now that part is very, very important. Okay. That this idea is very important for many topics we're going to discuss. Okay. So just keep this at the back of your head when we discuss images. Okay. Now, this class is a more of an experimental thing for me. I don't know for sure what's the right approach or what you say, what might work. Okay, so we'll have more interaction from the next session, I guess. But for today, I'll just do a basic setup. Okay, basic session. I want to just remind you of a few things now. I think you remember this. This is how we perceive objects. Light, is emitted from a point and then it hits some object and then it comes in a line and then hits your eyes. Okay, but I think you remember this. I don't know whether I told you last year. This was never the case. For a long time, people actually thought we saw objects in a completely different way. Like, for example, people thought that there was some fire in our eyes, okay, and the eyes emitted some rays which went and hit the objects, and that's how we saw the objects. Okay, now that sounds stupid, a lot stupid, but it made sense to them. This was the theory of Aristotle, by the way. Just saying. Okay, it was the theory of Aristotle that the way we see objects is, we our eyes emit light. So that is really stupid, but then we've come a long way since then. Okay. Now, leaving that aside, you guys know these terminology. I believe there's convergent rays, divergent rays, and parallel rays. There's nothing much there. Okay. Now, this is important. Listen up. So we discussed this. Fire was said to be Aphrodite. Yeah, yeah, the goddess of beauty. Yes, yes, that's good. Good, someone. Okay, I think we did this problem in 8th standard as well as last year. Some of you might remember this. There are two towns, and how many of you remember this problem? Yeah, I gave chocolates to some of you, and I hope everybody got it. I don't know. Whoever was supposed to get it got it, I guess. Okay. Okay, you're not getting chocolates, okay? I can't come down to your houses and distribute individually. That's not happening. Okay. Anyways, yeah. So okay. For those of you who are new to this problem is very important. There are two towns, town A and town B. Okay, just give me a yes or no of how many of you know this problem already. How many of you know about this problem and its solution? In the yes or no or in the comments, anything is fine. Come on, I'm waiting for your votes. Okay, a small portion doesn't know. Okay, okay, okay. Some of you know about it. Cool. So whoever have taught optics know about this problem. Okay, before this. Okay, Nihat doesn't know. Chirag. Okay, okay. Okay, that makes sense because I've not taught some of you guys. Now, here's the thing. Here's a detail that you need to know. There are two towns, town A and town B. Guys, others, you have to bear with me, okay, for the day. There'll be a lot of things that I'll be introducing. That's for those people who are new, okay, who are seeing these things for the first time. Okay. First things first, there are two towns, town A and town B, okay? And these two towns are next to an ocean, next to the sea, okay? Now, here's the details we know. This is town A. Town A is 5 kilometers away from the shore, and town B is 3 kilometers away. Okay, and both the towns are horizontal like this, horizontally separated by 6 kilometers. These are details you know. Now, here's the thing: the the entire council decides to build a pier. I don't know you know what's a pier. The thing is, it's a place where you walk into the a long ramp-like thing structure which goes into the ocean. Okay, so you can view the ocean. That's all. So they want to build it, but they don't know where to build it along the ocean. Okay, they can build it here, they can build it here where you see, they can build it anywhere. But the problem is once they build it, they need to construct roads to this place, right? Wherever they construct it, they need to construct roads to them. And they're kilometers away, so they have to construct roads. Now the thing is, let's assume they construct straight lined roads that are in straight lines. The question is, now there's one more detail you need to know, is that the council that builds these roads is a little conjus. Okay, I mean that's the word we could use. It's just that it doesn't want to spend a lot of money. Okay, which means it doesn't want to build a lengthy road. It wants to use least road material as possible. Okay, now it can build the pier here, then it's going to get this much road length. From this town you'll have this much length of road, and again this much length backwards. And it's possible that they can build it somewhere else. They could build it probably here. Okay, they could build it anywhere. Oh, so you're saying 90 degrees? No, that won't be the case. So I'll give an ink drawing so that you get an idea here. I think I'll be able to draw, but I'm not sure. I'm not using a pen, so this will be hard. So you could probably build the pier here, okay, and get a road length, this much road length. Or worst case scenario, you can build a pier here and you can get a crazy road length of this much. This is too much. The question is, what is the least road length that can work, and where should they build the pier? That's the question. Did everybody get this question? Whoever did not have an idea, can you give me a yes or no? Whoever did not know about this problem, did you get the problem? You have to give me the length of the road that will be constructed such that it's the shortest distance. Yes. Turns out whoever answered the 90-degree thing, no, it won't be at 90 degrees. I'm sorry. Okay, work on it. Work on it. That's the problem. Okay, you guys can take your time. Once again, I'll clear it. Did everybody get the problem? Or can you give me a yes or no now? Because there was an issue. I'm really sorry. So my message settings is to use not everyone. Once again, you guys have to change settings there. You can send it to me or anyone. You can't send it. Okay, okay. Privately, you can message me, right? Yes, cool. Okay, so everybody knows about this problem. Cool. So just work on this. I'll give you 1 day's time for others. Most of you know the solution to this, but yeah. There's a variant of this problem that is, I think you remember this, and people got chocolates for this actually, if you remember. It was not for the previous problem, if I remember. The chocolates was for this. There are two bases, base A and base B. So a military van has to go from base A to country A's border and pick up some package like this, come here, and then go to the second country's border, pick up a package here and go back there, okay, to base B. The problem is they can pick the package wherever they want. They can pick it anywhere along this line. And even in country B, they can pick it anywhere they want. Okay. So the question is, where should they go? Where should I pick the package so that they get to spend the least amount of fuel? Okay. You understand there's a lot of fuel that's going to be spent in traveling, right? So the question is, where should they collect the package so that they spend the least amount of fuel? Okay. These problems are very important for this year, for what we were discussing. Last year, they were introductory, but this year, they're very important. Like, for example, you could have collected packages like this, or you could even collect it like this. This is also possible. The question is, which is the most optimal path? What is its length? I hope you get that. Okay. Now, with that being said, here are the details we know. Base B is 6 kilometers from the base. Okay. For those of you who are seeing this problem for the first time, please take down the details so that you can work it out later. Okay, it is 6 kilometer, base B is 6 kilometer from country B, and 12 kilometers from country A vertically, 9 kilometers base A from country B, and 8 kilometers from country A. Okay, these are the details you have. Question is, you got to construct a road that is of minimal length, but that connects, but goes to both the borders and returns to base B. Not to construct a road, basically travel. Okay, let's assume that this is some sort of desert and you can travel anywhere you want. Okay, just keep this at the back of your heads. This is one interesting problem to work out. Okay, do you guys know about this FET simulations? I think you guys know about FET simulations, right? Yeah, this FET simulation. So what we'll be discussing today is the law of refraction. Okay, the basics of it, just to remind you what you studied last year. I think I'll be able to share the screen 1 second. If I'm not wrong, where is the browser? Where is the browser? Yep, there we go. So I hope you know about this FET. Can you see the browser? Can you see the browser? Okay. Can you guys see the browser? Yes. Yes, cool. Okay. Now, the thing is, something that you need to know, this is important, is that first things first, when I switch on the laser here, you see that the ray of light enters the medium and then bends towards the normal. So light ray comes in. I think you studied this last year, I believe, that when light ray comes in, it bends towards the normal. This is a normal to the surface, and you have a surface. So this is some denser medium like the glass, and this is a rarer medium. Now, the key important takeaway is you can see here something very interesting. As I keep bending the light, you see the amount of intensity of light that you get. So initially, you see that almost all the light goes through. When I keep it perpendicular like this, you can see 100, okay, 99%, almost 99% of the light goes through. Okay, it won't be still 100% because there'll be some reflection that happens on the surface. Then as I turn it, you will see more and more light gets reflected. Okay, more and more light gets reflected. As I change the angle further and further, you will see this light that gets refracted goes to about 76%. It reduces. The point is, it can keep reducing further, okay, as we go more and more. It's just 23% now, okay? So as the angle increases, you see the refracted ray intensity goes on decreasing, but the intensity of the reflected ray goes on increasing, okay? This top ray obeys the law of reflection. It obeys the law of reflection continuously, okay? And I think most of you knew about this. So this is critical. Okay, this is very important. I need these ideas later. Okay, so this is basic refraction, and you guys have studied this last year. I'm just going to go through it because I need for surfaces. Okay, regarding the presentation, where is it now? 1 second. Yeah. Do you guys have any doubts about that? About refraction? Can you give me a yes or no? If you have any doubts, you can ask now. Do you guys have any doubts? No. Okay. What about others? If anybody has any doubts, they can ask now as a question. Okay, cool. You guys know this. Okay. Yeah, cool. Okay. Now, how many of you know about Fermat's principle of least time? Give me a vote. 1 second. Don't give me a vote now. 1 second. Now give me a vote. How many of you know about Fermat's principle of least time? If you know it, give a yes. Otherwise, no. Okay. So I introduce optics using this every year, and some of you know about this. Some of you have never heard about it. Okay. Oh, hi Nihal, it's been long. Okay. What about others? It's a no. Okay, it's a no. Okay, fine. So I'll explain this. So what it says is, it's in the simplest words, it says, if light, and this is the most important part, if part, okay, if light has gone from point A to point B, you'll observe that then it has taken the shortest, then it has taken a path that takes the least amount of time. Okay. In fact, this statement is more powerful than all the laws you have studied, even Snell's law or any other law that you have studied. If light travels from point A to point B, it will have traveled in such a way that it takes the least amount of time. Okay. Now, this is not part of your syllabus as such, but this is critical for introduction. This is the idea behind most of the things that you're going to be studying. So it's important. So I'll be introducing it using Fermat's principle, whatever I'm going to introduce later. Okay. Going ahead, here's the thing. So if you look at this example of a mirror, okay, if you have a mirror and if light bounces between 2 points, you will see mirror can reflect light about any point. Let's say Look at this. For example, 1 second, observe this. See, light arriving at from point A, going to point B, could have bounced any way it wants. Okay, but it just so happens it chooses a path perfectly, and you might say it obeys the laws of reflection. Yeah, this was there in ninth standard, if you remember. This was in ninth standard because this is the basic introduction for what do you say, the optics. Okay, and most of them do not know about it because yeah, this was not part of a textbook as such. Okay, so if you see, some of you might say light obeys the law of reflection. Okay, obeys the law of reflection. But to be honest, that's to be honest, there's much more deeper happening. You can simply say law. You can throw away the law of reflection and say light is simply obeying the Fermat's principle. Okay, light simply obeys only the Fermat's principle. Yes, you can say that the law of reflection comes from Fermat's law. Okay, Fermat is more important. So basically, the idea is that if you look at it, if light goes like this, don't you think it will take a lot of time? Don't you guys think it will take a lot of time? Yes. So the thing is, it has to take a path. Even it can't go even like this. This is too much. This takes really long, crazy long. So it will take a path which will take the least amount of time, and that happens to obey the law of reflection. It just so happens. Okay. So it's a much more powerful law, and light seems to obey it always, no matter what. Okay. Yeah. Now going ahead with that. So here you can see an idea of what's happening. I won't explain this much because that's a clue to solving a problem later. So that's why I'm going to leave it. For those of you who are trying it, I'm just going to leave it as an exercise. Okay. There's few things I need to add from last year. That is the diffuse reflection, if you remember. For most part, you see our surfaces we deal with are irregular, and that light always undergoes diffuse reflection. It spreads outward. Okay. You don't see, okay, what do you say, the law of actually, if you look at it, the law of reflection is obeyed on each piece of this surface. Okay, but it's just that the piece is made up of many pieces. What do you say, many the surface is made up of many subsurfaces, smaller surfaces. Okay, so I think we discussed this, right? We discussed about the smooth paper. If you know, this was a surface of a paper, even though it's not a smooth surface. Okay, it just happens to, what do you say, uh, it does diffuse reflection because there are so many surfaces at the micro level. Okay, light gets scattered in all directions, so you never see your image in the paper, even though you never see your image in the paper, right? Because you know, light doesn't obey perfectly the law of reflection. I think I discussed this, that antennas are smooth surfaces for some reason, if you remember. This I think you remember. And we also discussed this. This is about how light gets bounced off. Why do you see this? The question is, why do you see this? Okay, can anyone explain me this? Why do you see such lines like this? Can anyone explain me that from last year? In the comments, in the comments, in the chat, in the chat. If you think you have an explanation for why we see this lights like this in water, on water. I wouldn't expect a lengthy answer. I just need 3-4 words. That's all. What do you think they are? Okay. Reflection. Yeah, it's a reflection. It's not a refraction. I can assure you, it's not a refraction. Light bounces off from the surface. I told you, right? Most of the light bounces off the surface. So if you look at that earlier image, if you see here earlier this thing, you might have seen that see, if you look at it, most of the light bounces off the surface. About, when it comes at a shallow angle, about 68% of the light actually bounces off the surface and going into the water, okay, or any other surface. So most of the light actually bounces off and goes towards the person who's viewing it. Okay. Those are shadows. No, they're not shadows. They're not shadows. I'm sorry. They're not shadows. The water causes reflection to occur a lot, and okay, at different angles. I guess the surface of water has a lot of bumps which reflects water at different angles. Thomas principle? No. Okay. So one of the answers that's right and makes the most sense for me is Medan's answer, which says that light reflection happens at different angles. And many say, yeah, water is not still. Yes, scattering of light. Okay, I'll put it in the mild sense this way, if this works for you guys. So what's happening is something like this. Okay, I need a black screen. 1 second, if possible, I can get a screen. Um, yeah, I think white screen will do. So basically, you have the water surface, and this is you. I'm going to put a big Y. That works. That's you. Okay. Okay. That's skeleton. And there's a building here. Okay. This, I'm sorry, I don't have a pen right now. I think I might need a pen for the next time. But I'll just stick to this for now. Yes, the surface of water as, yes, yes. Okay. That makes sense. Now I'll explain something very important. So let's say this is the source. You're trying to observe this. Okay. And this is my point E, let's say. Okay. I'm trying to observe this. Okay, now what happens is, since the water surface is not, steady, you have multiple surfaces, like, let's say many surfaces. So here at this point, you have a different surface like this. This surface is at this angle and some other surface is at completely different angle. I hope you get that. The surfaces are at different angles. Okay. Now, when the light from point E comes downward, let's say I'll use a different color for that, if possible. So when it comes in, not total internal reflection, you guys are throwing answers in the air now. So when the light comes in, if the surface is flat, it will obey law of reflection and come to your eye straight away. And you will think the building is here because, this is where you think that point E is. And hope you get that. Why you will think that the point E is here? Because the image is formed there. For you, the light travels in straight lines, so you think that the light is coming from this point. Okay, light was actually, 1 second, I need to change the pointer. So here's the thing. See, if you look at it, light comes from this point and hits the surface here and bounces off. But then your eyes are like, look, light came to me in a straight line. Light came to me in a straight line. So it must have come from this point E. Okay, so your eyes perceive the building to be here underwater. Okay, at that point, at that place, at that location. Okay, but there is one more detail. Now, since there are many surfaces, what will happen is this. 1 second, I need to use a pen. I have to switch between a pen. I'm sorry. Yes, now. So what happens is, let's say there will be light bouncing off from here also. But then since the surface here also is in that angle, in a perfect angle, so that the light ray bounces off to your eyes itself, even from there, even from this location, it bounces off. So even let's say a surface here, the light comes in, bounces off, and then goes at an angle. So your eyes think that light is coming from all the points. It thinks that the building is here, everywhere, or at all these locations. Okay, so you start seeing that one light source called point E at all points on the water. You start seeing it almost everywhere. Okay, so that's the reason for this image that you see. So if you look at it here, this blue color light which you see, the blue color, 1 second, I'll use a laser pointer thing. So if you look at this, wait a second. Yeah, if you see this blue light, can you see this blue line of light? It's seen everywhere. You can see it everywhere along the water. But that's coming from this one location. That's it. That one location. It's hitting that surface and bouncing off and hitting your eyes. Even here, water, it comes here and hits a water surface, which is at a different angle, and comes to your eyes. Now, along this whole line, there are water surfaces which are perfectly aligned, so that they're aligned in all directions. That you start seeing the source of light, that's blue source of light, everywhere along that line. Is this clear to you guys? Most of you had different answers, but some of your answers were right. Yeah, I believe Samant and I think Medan had an answer that was the most closest, and Nidhi also. Yeah, water still. Yeah, is everybody clear with this? Just give me a yes or no so that I get an idea. 1 second. I'll clear off. Okay, yes or no works now. Okay, this is clear. Okay, cool. So this is a good batch. Okay, fine. You might have seen this also. Anyways, now here you don't seem to see that. So if you have a light source somewhere on the top of this location, you won't see that light source everywhere. You only see it here. Okay, do you see that? You see only the image of the tip of the tower only in this location, not everywhere along that line. Okay, that's because the water is still. And as Nidhi said, yes, the water is still. And here's the thing, if the water wasn't still, yeah, you might have seen it everywhere. So the jittery water creates a lot of surfaces which reflect at every point. There'll be one surface of water. Yeah, it's not a smoother surface. I would say it's yeah, good argument. Yeah, it's a smooth surface, and this acts like a mirror now. This is what mirrors are basically. Okay, uh, reflection only, specular reflection. This is called specular reflection, and this is important. I think I mentioned this. Uh, I want to know how many of you remember this explanation. Streets appear darker. Streets appear darker whenever, uh, whenever it rains. After it rains, streets always appear darker. Have you known this? Have you observed this? Streets usually appear darker once it rains. How many of you think it is the case? How many think this is true? Uh, can anyone tell me why? If you know it is true. If you remember it, yeah, you might remember it, but why? Why do streets appear darker after it rains? What would happen if there was a lamp or something in the previous pic? Which one? Yes, even if there was a lamp, you would see only one image of that lamp. You wouldn't see multiple images. You wouldn't see it everywhere along the water. Okay, you would see it in one location. Okay, that clarifies your doubt, I guess. Okay, many of you have different answers. One second. Some are saying, wait. What's the answer? Because light only specific to locations and are less probability of reaching eye. No. Reflects only to specific locations. Okay. Muralidhara is a correct answer. What reflects more light than before? No. Okay, there's a lot of answers. One second. No, it's not because water absorbs. Maybe because clouds. Nope. Okay. Many have ideas that it smoothens. So yes. Now here's the thing. If during a daytime you see that light hits these surfaces, like for example here, and comes to your eye from every point. Okay, comes to your eye from every point. So you get light from the entire street. Okay, that's because there's no rain, it's like mirror and light is concentrated. Yes, something like that. So you get scattering from all directions, but when it rains, after it rains, you see only specular reflection. You get reflection only along this line. Okay, so from this side, you won't get the sunlight coming. Light won't from the sun won't bounce to this point and then come to your eye. It'll just come from these locations. So at night also, see, it appears slightly darker compared to this picture. In fact, in video games, this is when you're designing, what do you say, worlds like where you want to keep the, let's say Avengers and all, when you're doing animation and you want to keep it really perfect. This is for Nidhi, by the way. It's what you say, people care about this a lot. They make sure it appears darker. Okay, after it rains. So if you played Need for Speed or any of these games, I don't know which games you guys play, but if you have played Need for Speed or in any game environment, after it rains, they try to make it slightly darker, the surfaces. Okay, NFS, yeah, some of you might have played NFS. Fortnite, yes. How does the water smoothen the surface? Okay, the water does not smoothen the surface. It's the thing is, earlier reflection was happening on the ground, on every point on the ground. Now it's happening on the surface of water. Earlier reflection was happening on the ground. Light was bouncing off the ground, which has irregularities. But now it's like water is like a smooth surface, right? So most of the reflection happens from those points. So I think that's one explanation I could give. Hope that's fine. Okay. What about others? It provides fills up. Yes, cool. Okay, nice. Yeah, there are some images. You can check this out. Okay. There is one more problem, and I've given this, and I think we killed May last year and her friend. I don't remember exactly. Yeah, because of this problem. Yeah, I'll give this problem. Just work it out. And some of you have given me the solution. Okay, some of you were right. I think two of them gave the solution. How many of you remember this problem? Give me a yes or no. How many of you know the solution also? How many of you, okay, if you don't know, give me a no, because that's important for me. I'm looking for the no's. No for both. Okay, awesome. Okay, there are a bunch of people who do not know this. Okay, so I'll have to explain. I am really sorry for those of you who are listening who knew about this. Okay, really sorry. So here's the thing. So there is, let's say, someone. Yeah, there was a snake last time, and yeah, I remember that. We'll go with a crazy example. You give me the suggestions in the comments. What danger are we going to pose to the person right now? What do you suggest? Anaconda? Okay, Fermary. Okay, nice. Okay, awesome. That's good. We'll go with it. That's fine. Nuclear radiation. Okay, T-Rex. No. Okay, so let's say you're camping somewhere in some remote location with your friend, and turns out this is an entire big ground. Okay, there's a ground, and you're camped there. Next to you, 60 meters away, just 60 meters away, there is a forest. Okay, slightly thick forest. So your friend decides, your friend's name you can suggest. Give me a name for a friend. Your name, you have to suggest your name. You'll be the friend in the comments. Okay, nobody volunteers. Okay, Samant is fine. Okay, Samant. So Samant, who's your friend, goes into the forest. Okay, and okay, Muralidhar is behind him. He's in the camp. He's the other friend. Okay, so what happens is, here's what happens. So Muralidhar, okay, let's say I don't want to be fall in danger. Okay, awesome, nice. Okay, so Samant enters the forest, and he was playing around. He was doing some explorations, and he reaches this location. Okay, this location, and there he happens to meet another friend. Okay, and from the suggestions that have come, it's I think anaconda, or someone's preferring permaris. Okay, that's good. We'll go with permari. Okay, so we have a python or some sort of snake there, and someone can't rescue him, save himself, and he yells at Muralidhar. And Muralidhar, being the best friend in the world, which I think he is, I don't know. Okay, he runs from the camp to save Samant. Okay, now there is a problem. You guys have to help Samant reach. What do you say? Help Muralidhar reach Samant. Okay, yeah, yeah. Muralidhar is so kind. I think deep within he wishes you die, but yeah. Anyways, so the thing is, from the camp, uh, Muralidhar has to run and then reach his friend. But there's a problem. Here's the plot twist. See, Muralidhar on the land, that is in the ground, he can run really fast. He can run at 4 meters per second. Okay, he's really fast. That's cool. But then there's a problem in the field, in this forest region. There's a problem. He can run only at 3 meters per second. The question is, he has to run the quickest before the anaconda starts kissing, Samant. Okay, so the question is, which is the fastest way to reach there? Okay, should he go straight in a line and run like this? Is that a great idea? Like, for example, okay, I'll give you 3 suggestions. Which one do you think is, you guys have to give me an answer. I'll give you 3 possibilities. One is like this possibility. Other one is a straight line like this. A third possibility is something like this. This is Muralidhar simply running off and waiting so that he dies. But there are other possibilities. One possibility could be, he could go like this and then come there. Okay. So the question is, which one would be the possibility? I'll give you the names for this. This will be A, this will be B, this will be C, and this will be D. Which one do you think is the best way to run so that it reaches the quickest? Okay, many have suggestions. Okay, some are suggesting B. B is a straight line, okay? Oh, by the way, I'm still drawing, sorry. Okay, I can't erase that for some reason. Yes, go. Okay. What are your suggestions? I didn't get it. Okay. Many are saying A, some are saying B. Does anybody want to take D? Okay, some are suggesting that Muralidhar take D. They really want someone to die badly. Okay. Anyways, many are saying A, but some are saying D. Nice. Anika, nice. Okay, D. Okay. You really want to kill someone. What about others? There's A's, there's B's. Okay. Most are saying A's and B's. Some are saying straight lines. Okay, okay. Oh, someone's suggesting this. Okay, someone suggesting this. How many of you think this would be the best idea? Okay, I'll draw it 1 second. How many of you think come straight away like this in a straight line and then enter the forest here with the shortest distance? How many of you think this is the E way, the Eth way? Or E, the letter E. Okay. How many of you think this is the best way among all these paths? Okay, okay, okay. Some are saying E is better. Some are saying going with. Okay, Samant is dying, by the way. He's making sounds in the chats. Okay, like and all this stuff. Anyways, okay, 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 okay. He's dying. Yeah. I think in the decision process he'll die by now. Anaconda would have kissed him enough. But yeah. Okay, now going ahead, some are saying B. Okay, so many are sticking with B. Okay, turns out I'll tell you what could be an answer later, but some of you have suggestions, some of you seen this problem before, and yeah, some of you know the answer. But yeah, we'll come to this problem later. I'll discuss. Oh, someone is saying, Muralidhar, can you get a gun, please? Yeah. Okay, please. Yeah, that's one suggestion. Okay, going ahead. I think you know about this. Light travels the fastest in vacuum, goes from an optical denser to a rare medium, and light bends. You know this, right? So this is basic reflection. And I think you remember this law, that is this angle of incidence, angle of refraction. And always, in this case, you can see it's going from an air medium to a denser medium. So it'll bend towards a normal. Oh, Vivek has another suggestion, kill someone. Okay, nice. Okay. Okay, going ahead. So this I think was important. Okay, so the question is, when refraction happens, what happens to the wavelength? Okay, what happens to the wavelength? One second, give me a moment. This is going to take some time. Laser pointer, yes. So about wavelength, what does it do to the wavelength? Here's some interesting ideas. Okay, how many of you think, what do you think happens to the frequency of light when it goes from one medium to the other? What do you think that happens? Do you think it changes or not? If you think it changes, say changes. Frequency of light. Increases or decreases, that's second suggestion. If it changes, say increases or decreases. Some are saying changes, some are saying not changes. Okay, okay, cool. Okay, I'm saying if light goes from one medium to the other, let's say it goes from a rarer to a denser medium. Do you think the frequency of light changes? Does it increase or decrease as it goes from one medium to the other? Frequency of light, frequency of light. Okay, now I have a follow-up question to some of you who can think a little bit deeper. Depends on the medium. Okay, okay, fine. I'm giving you the glass medium. Okay, so here's the simple question, follow-up question. What determines the color of light? Is it okay? I have a question for those of you who said the frequency changes. That wave. Okay, what about wavelength? Before that, what about wavelength? What about wavelength? Okay, okay, cool, Anika. Yeah, Anvita. Yeah, yeah. I don't think it changes. Okay. What about others? What do you think about frequency? Chuck frequency. What about wavelength? Do you think wavelength changes when it goes from one medium to the other? Does it decrease, increase? Okay, I'm saying it goes from a rarer medium to a denser medium. Does it increase or decrease, or does it doesn't change? One of the options. Which one do you think it is? Okay, people have many suggestions. Okay. I'm surprised that there are so many varying answers. Like there is half of you saying it doesn't change. Then there is another one third of you something decreasing and some portion saying increasing. So, so it's a lot, to be honest. Okay. Okay, I have a question now. This is a follow-up question, and some of you know the answer to this. Okay. And I think one of you answered this. I forgot who's that. I really forgot who answered that. Yeah, Sumit answered it right perfectly. But I'll just go ahead. Okay. So here's the thing. What determines the color of light? So let's say when you see red color, okay, so you see a color and you see it's red. What determines that color? Is it the frequency of light, frequency of red color, or is it the wavelength? When you call something red, is it determined by its wavelength of 600 nanometers? By the way, we say 600 nanometers is roughly the wavelength of light. And frequency of light, you can calculate correspondingly, okay? Some into the 10 to the power 14 hertz. The question is, which of these two properties determines the color of light? So when you see red color, like this pointer on the screen that you see, it's red. What determines it? How many of you think it's wavelength? How many of you think it's frequency? Okay, okay. Why do you say it's frequency? Whoever is saying frequency, can you tell me why? Why it's frequency? Can you tell me why? Why it's frequency? Yeah. Muralidhar, that's kind of the idea I gave you, but it's not exactly the thing. It's just that our eyes interact using certain electrons and oscillations in the eyes, right? Basically, there'll be some absorption that will be happening in the eyes. Yeah. Yeah, you've been taught. Yeah, yeah. So I'll put it in the simplest sense. And this is a very loose terminology. Do not take my word for it as it is. always understand there is a much more mathematical and deeper explanation to what I'm going to say. So when light enters your eyes, hits your eyes, uh, how do we interpret color is because the light interacts with some atoms in our eyes. Okay, there are many assumptions. I won't go into that. It interacts with the atoms in our eyes. Okay, and it basically involves these atoms go into certain kind of oscillations. Okay, which means oscillations depending on the frequency of light, how frequently they get bombarded with peaks. Okay, so based on how many times it receives the peaks per second, it's going to jump around the electrons or atoms or whatever in our eyes. So what we see as color is determined by frequency. Okay, it's not by wavelength, it's determined by frequency. Now here's the important takeaway. If it's determined by frequency, then I have a question. Is this possible? Is this possible if it's defined by frequency? And if frequency can change, some of you suggested that frequency can change in the water medium. Then let's say I send red light, red laser into water or glass. Okay. Now, as it goes through the medium, it bends. You know that part. Okay. Nice. Now, here's a question. When it goes through the, what do you say? When it goes through the medium, do you think the color of light changes? Do you think the red color laser changes from red to something else because frequency changes? You've not seen that happen, right? You've never seen that happen. Whenever you point a laser, the color never changes. Yes. So the key point I'm trying to make is the frequency does not change when you go from one medium to the other. Okay, just keep this at the back of your head. You've never seen it because frequency never changes. At least for now, for what we are discussing now, it doesn't change. Okay, there is higher order physics where things can change. There are certain advanced topics, but for now, on the basic surface level, from Snell's law point of view and everything else, from high school physics point of view, yes, it does not change. Frequency does not change, but wavelength changes. Okay. Now, what does wavelength change look like? So there's a visualization that might help you with it. I can't share the screen. 1 second. Yes, now there you go. I hope you can see this. This is by University of, I think, yeah, School of Physics at UNSW. So there's a visualization of what happens as light enters a medium. So if you look at it here, light rays, they have a wavelength of this much distance. What you see here, this is the distance between the peaks. So these lines represent the peaks. Okay, yeah. Now here's the thing. Here's the important thing. As it enters, you'll observe something interesting. The rays, the peaks tend to get compressed closer and closer. Okay, but if you look at this oscillatory frequency, this frequency, it doesn't change. It doesn't change. It oscillates the same amount even if I pick a peak here. Okay, so frequency does not change. It oscillates the same amount, but the wavelength, the gap between this thing, what is that? Between the peaks shrinks. So the wavelength shrinks. And here's one more interesting thing. There's also change in the direction of the rays, the lines. You see there's a change in direction. So like this is one, I don't know, not a dumb explanation. It is a almost convincing explanation given usually for why light bends. Okay, this direction change that happens. If the wavelength changes, okay, there's a question. If the wavelength changes, then the speed of light changes. But isn't speed of light a constant? Okay, Muralidhar has a good question. If wavelength changes, so you can't. Okay, I'm not playing the animation. It stops quickly. Okay, I'm really, really sorry. Okay, now can you see the animation? Can you give me a yes or no? Can you see the animation? You can't see the animation. Can you see any screen? Wait. My browser, can you see my browser, right? You can see my browser. Can you see something moving, something? Light rays? Okay, 1 second. It doesn't play continuously, so I'll have to change something. 1 second, your internet will be used a lot now. For a moment, get ready. Okay, now, can you see it? Now, can you see it? The animation? Blurry, okay, now? Yes, this should be better. It's blurred. That's because of your internet. Okay, I'm really sorry. It's trying to push a lot. I don't think it's a problem for everywhere. The PPT is invisible. I've closed the PPT. I'm sorry. Okay. But here's the thing. Okay, I think that's clear. I'll switch back to low internet quality because it's gonna wreck. Yeah. So yeah, here's the thing. But where's the red bar? What's the red bar? Okay, the red bar here, which you see. One second. The red bar which you see. That's the intensity of the electric field at that point. At that point, what is the electric field intensity? Anvita, you were asking something. What was it? Oh, please. Okay, fine. Okay, the speed of light changes in different medium. Okay, now here's a very important question, which I wanted to get into, but I'll wait for a moment. It's a question by Muralidhar. Nidhi, you got the answer? Is that clear? Why the red bar exists? Okay, cool. Okay, going ahead. Where is it? Where is it? Where is it? Share screen. Yeah, slideshow. So wavelength changes. That is important. Satvika, the bending of the peak depends on the angle with the normal. Yes, yes. The change in direction depends on the angle. So that's called the Snell's law. Okay. Yeah. Now, how many of you know about this rig 2? How many of you know about rig 2 here? This one. Hey, is it blurry that bad? Come on. Is it blurry, the screen? Okay, 1 second. I'll check my internet. Check with my internet. Give me like, okay, you guys have to give me like some time to do a switch between the internet. Can you guys wait for yeah, 1 second, 1 second. You guys have to wait for 1 minute while I do a switch between my internet. Okay, 1 second. Okay, can you guys hear me? Give me a yes or no. Okay, okay, that should be clear. Uh, so we'll get started here. I think the internet is back. Okay, yeah. Is this better? Is this clear now? It's still blurry. Still blurry for some of you. Okay, okay. How badly blurry is this? Okay. Uh-oh. Okay, once again. Is it your internet? Can anyone see it clearly? Come on. Okay, 1 second, 1 second, 1 second. I'll just try to do something. Okay, now, can you tell me? How about now? How about now? Is this clear? This should be clear. Is this clear now? Okay, PPT. Can you see the PPT? Yes, 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 yes. Cool. Okay, I think I know what happened. It's okay, fine. Now here's the thing. Yeah. We'll get back. Okay. So how many of you know about this simulation? I think there was a optimizing for video clip. There's a setting in Zoom. Okay. Anyways. Okay. How many of you know about this simulator? rig2288.github.io. How many of you know about this? Can you give me a yes or no if you know about it? No. Most of you don't know. Some of you know about it. Okay. Now this is critical. Okay, this year and last year also, if possible. This is very, very important that you do this check out these simulations. I told it to you guys last year, but I don't think I emphasized as much. But this year I'm going to emphasize a lot since you guys are online. Okay. Uh, Here's the thing. Wait 1 second. I'll go to the browser. So there is a student from Korea. I think he was in high school like you guys when he did it. He developed a simulation. Okay, 1 second, I'll just share it with you guys. So he developed a simulator called an optic simulator. Okay, visualizer. So what it can do is you can add light sources. You can add your light sources, whatever you want. Okay, to this. I think you can see in the chat. Come on, where is it? Yes, I think I showed it. Yeah, he was a Korean student. You can adjust the brightness and the ray density. 1 second. You can add many sources. You can add glass planes and many things. I think I'll delete those. 1 second. You can add lenses. Probably you can add lenses. 1 second. I'll try to add a lens if possible. Where is lens now? Yeah, mirror. No, not mirror. Glasses. Ideal lens. So you'll see here there are lenses. Okay, so you can add cool things here and share with us. I'll share this link with you guys some other time in some time. But here's the thing. Yeah, so please play around with this simulation. Okay, he has done an excellent job with it, creating it. We can learn a lot from this. Okay, a lot from this. Okay, on how light behaves and how lenses will start behaving for us. So you can adjust the focal length and many other cool things. We'll come to this some other time, but for now I'm just going to introduce it to you. Okay, now just keep this at the back of your head. Rick 2, I'll send the link later. Someone remind me at the end of this class. Okay, someone remind me at the end of this class when we end to send you the link. Okay, yeah, cool. Going ahead, there's also always this not so convincing, but an explanation given for why light bends when it goes from one medium to the other. That is, imagine you're, let's say, rolling a, what do you say? I hope you remember this example, some of you. We can see the link. Yeah, it's there. I know you took a screenshot. Okay, cool. But I'll send it for others. Just remind me. Okay. Now, whenever, let's say you have a, let's say, a toy with wheels and you're rolling it on a sidewalk. As you roll it, can you guys see this? Oh, we're still in the browser. I'm sorry. I think you remember this. Yeah. Here it is. I'm sorry. I think this is visible. Yes. Now, here's the thing. Oh, I'm losing chat. Yes, clear. Okay, now if you see it, I think you remember this. If you roll this toy over the sidewalk, when it enters a grass medium, you will see that, what do you say? You will see it bending, right? You will see some sort of, this wheel will start moving slower, whereas this wheel starts moving faster, which ends up giving it a turn, a small turn. Okay, if you remember this, which eventually leads to, let's say, which kind of eventually leads to, what you say, the movement that you see here. So this is one strange example that was there why light bends, but not the best one. It's a ray picture. Okay, so this is on the wavefront picture, what it looks like. Okay, yeah. Going ahead, I think you know about the law of reflection. Sin I by sin r is equal to k. I think you know this. This is Snell's law. You don't need this year. Okay, just a reminder. You don't need it this year, but a reminder. I think you also know this. The speed of light. It just so happens the speed of light changes when it goes from one medium to the other. Okay, it changes when it goes from one medium to the other, and the ratio of that speed of light gives you the refractive index of the mediums. Okay. I won't explain this in much depth because it's not much needed this year. I think you guys know about this Coca-Cola bottle example where there is a visualization. How many of you know about this? I don't know whether I showed it to you guys. Yes. Okay, most of you remember. There's a video by MIT where they show light moving through a Coca-Cola bottle. Okay, light moving through a Coca-Cola bottle. Okay. Actually, it's beautiful to watch. I think we can share it. Once again, I'll try to open it. It's fine. I think I can show it to you. This. Okay, I forgot the link. I'm sorry. We'll do it some other time. I'll show it to you some other time. Okay. Now, coming to the point. Skip this part. I think I suggested to watch this. I suggested most of you to watch this number 5 video on why light travels slower through glass. Okay. Now, the explanation for this is very, very complicated. Didn't understand why I saw this. Yeah. So after you watch this video, you will be more confused. Yeah, you won't be able to get it to some extent. Yes, as you see in the chat. The thing is, but I want you to watch it. It's 16 minutes, not today, but later you can watch it. It's on YouTube. It's by 60 Symbols. It's a great video. Okay, I can't show it to you here, but it's going to explain you why light travels slower through glass. But and here's the best part: it's not that simple. Okay, it's not really that simple. Does anybody have a possible explanation for why light travels slower through glass? Can you can turn on your mics and start speaking? Whoever wants to give a possible explanation. Does anybody have an explanation to give? Why do you think? An hypothesis. Hypothesis. Yes, that's a link, Samant. Yeah, you sent it. Uh, the problem with the Zoom chat is you can't. It doesn't highlight hyperlinks. Okay. Okay, someone is saying because glass is denser. Okay. Why do you think density slows light? Okay, some of you know, Samant knows. Okay. Can you turn on the microphone and speak? Why? A possible explanation. Okay. Okay, cool. Mic can't be turned on. Uh-oh. I don't get why is that. Oh, okay, now, can you unmute yourself and speak? Now it works. Yeah. Whoever wants to give an explanation, just speak to the mic. Okay, possible explanation. The microphone is, you can turn on your microphones. Okay, somebody's speaking. I don't know who. Okay, some have simply opened their microphones.
Hello.
Okay.
Can you hear me?
Yeah, I can hear you. Come on, tell me.
Nice to meet you, sir. It's been such a long time. I remember you still.
Okay.
Reporting later.
Okay. Listen. Tell me about the explanation. What do you think is the explanation? Yeah.
Yeah. Now, when light travels through any of these mediums, the individual atoms of those mediums, they absorb the light and give it out again. And this, like, there's a delay in between the absorbing and giving it out. So the denser, the more particles there are, and more times this process repeats. So in denser mediums, it is much slower, whereas in vacuum, there's nothing to absorb and slow it down. So it is at max speed.
Okay. So you're saying there's a process where there's absorption and there's a process of what you say atoms interacting with light, and since there are more atoms and okay, that's a good explanation. Yeah, that's one of the plausible explanations, but there are many. Okay, there are many. That video will give you multiple of them, and the last one is crazy. Okay, the last explanation is very crazy, but I personally recommend you check it out. Okay, yeah. Anyways, I think I'll mute all of you for now. Thanks for the explanations, whoever gave it. We'll go ahead. Okay, we'll go ahead. So, okay, 1 second, we'll have to mute you guys, I guess. Okay, that's fine. That's cool now. Okay, nice. Yeah, now it's better. Okay, so this explanation, why it'll bum me off, is because there are multiple explanations. What Samant told just now, that was an interesting explanation. Basically, the idea is that maybe there's some sort of absorption happening between the atoms, and light. There's some interaction happening between the atoms and light, and this interaction keeps happening, which slows down the light. Okay, but some of you might ask, isn't there a rule that speed of light is a constant? What about that? What about the fact that speed of light is considered to be constant? Okay, someone saying no, it isn't. Oh, someone saying in vacuum. Okay, only in vacuum. Yeah, so when we say speed of light is a constant, yes, we say speed of light is constant only in vacuum. But here's the most important part, and this is quite interesting for some of you, I guess. Speed of light is not about light. Okay, speed of light is not exactly about light. This limit, the limit on speed of light, which says that 3 lakh or 299, whatever number we have, that actually is a limit on speed of information. Okay, Samant, what is that? Yeah, so it is a limit on what do you say, what can I say? Wait, it's a limit on the how fast information can go from one point to the other, or yeah, events can influence. Okay, it doesn't mean that light can travel slower than it. Light can travel slower than it. Speed of light is not a constant. Light can always travel slower. But the thing is, it's a rule on information. It says that information cannot travel from one point to the other faster than the speed of light. Okay, yeah, something like that. So it's a limit on information. Okay, that is might be deeper for you, but yeah, it's something. Okay. Yeah, as a homework, I'll give you something interesting to watch tomorrow for today. Okay, later, I'll do that later. I think you guys know about the Snell's law. This is a more general Snell's law, which says that Ni is the refractive index of the lower medium, and Nr is the refractive index of the refracting medium. I and R are the angle of incidence and the angle of refraction. Okay. Okay. Now, going ahead, there's some issue with the chat. Oh, Bose-Einstein condensates, yes, it can go much slower. Yes, it is said to be very slow, almost the speed of a bicycle in Bose-Einstein condensates. Yeah, I'll skip this part. This is fine. This we can deal with. I think you guys know this. At zero angle of incidence, light goes straight through without experiencing any bending. Okay, and I think you guys know about this. So yeah, problems. What? Yeah, this is one problem. That's it, nothing much. Okay, I want an answer for this. I want to see how many of you can get this. It's a puzzle. Okay, light from a filament bulb hits a surface. Okay, a glass slab hits a glass slab, and two images are seen of the light bulb. I think you have seen this before. When you see a glass slab, sometimes you see two images of one object, okay, of a light source. And turns out one of them is white in color, the other one is red among the two images. How can this happen? You can turn on your microphones and answer. Okay, one second, I'll give you the permission to. Okay, if you want to turn on your microphone, tell me in the chat first. Okay, that way I'll be able to give you the permission. Because of refraction, nope. Okay. You can turn on your microphones, whoever wants to tell. Yes, now. Who wants to get? Okay, some of you didn't get the question. Okay, wait a second. Before you guys give the answer, I'll just explain it in a better way. What's happening is you have some glass slab on the table. Okay, you have glass slab on the table, and the light is coming and hitting that glass slab. So you see there's a light source in the room, and you're seeing that, what do you say? You're seeing the image of the light source on the glass slab. Okay, but then on the glass slab you're seeing two images, and one image is white in that because the light source is white. Second one is red. The question is, how is this possible? How is it possible that one image is red, one image is white? Okay, yeah, I'll see your answers before that. So some of you said you didn't understand the question. Okay, surface of the glass slab or partial reflect, Pratyusha. Okay, that's good. Light splits while refracting twice. Not exactly, because the frequency during refraction, frequency does not change. I told you when refraction happens. Someone's saying diffraction. Okay. Does anybody have an answer? It's a puzzle, actually. It's a puzzle, to be honest. Reflection of light from the glass surface of the glass slab. Yeah, Samant has a very close answer. I think even Pratyusha has a very close answer. Yes. Okay, I'll give the explanation for why that happens. One possibility is this. You know, when light hits a glass surface, some light gets reflected from the surface. Yeah, some light gets reflected from the surface itself. So for example, let's say this is our surface. Observe this. Let's say this here is the surface, okay, where the light hits it. So when it comes to your eyes, this is your eye, let's say E, you will see white light because this is white in color. This is a white source that comes. You'll see that because light bounces off and hits your eyes. But then one more piece, a small portion of light goes inside and gets reflected from there. Okay, and then comes and hits your eyes, whichever ray that is going to come. It's going to come. Two rays are going to come. So that's why you see two images. The second image that you see is because from the second reflection at the second surface here inside the glass slab. Okay, now the other image could be red because of this possibility that maybe it gets absorbed. Maybe all the wavelengths which go inside get absorbed. Only red light passes through. Okay, maybe this glass surface absorbs all the wavelengths other than red, so it appears red. Okay, so that's one possibility. Okay, that's a puzzle. Okay, so I think most of you got it. Can you give me a yes or no? Does anybody have a doubt about it? Okay, cool. Why should glass absorb other wavelengths? Yeah, now again, it depends. So one possibility is, maybe this is a possibility, maybe glass atoms absorb all the colors but give out red. Okay, and that's why it appears red. That's one possibility. Or maybe there's an absorption of all the other wavelengths, only letting through red or some other color, but it appears red because red is more dominant. Red is more brighter, maybe. Okay, greater intensity. That's one possibility. Okay, what is so special about red? No, it need not be red. It could have been anything. Okay, it could have been any color. Our strips produced striped off and produced image that is red. Is it? Oh, no. Pratisha, your answer was right earlier. Okay. Would you see multiple images if you use a more intense? No, you would see only two images because there are only two reflecting surfaces. One question is, would you see multiple images if you use more intense source of light? No, you would see only two images because there is, what do you say, one here and one here. There are only two surfaces that reflect. Okay, only two surfaces where reflection happens. Okay, I hope that's clear. Okay. I think I'll go ahead. This is done. This is some basic things, fun part. Okay. Now this is the most critical part and probably the most important part for the day. Listen up. So I'm going to explore some interesting ideas about Fermat's principle of least time. Now I think I told you Fermat's principle of least time is the most important. What if there's continuous reflection? Continuously, it's possible. Yeah, that's possible, Medansh. If there would be another glass slab, there'll be 4 images. Yes, Satvika, yes, you're right. That's cool. Yeah, that is true. Now, here's the important thing. More exploration in the shortest paths. Now, this is important. Hope you know Fermat's principle of least time. What it says is, if light has gone from, let's say, point A to point B, some point B, then it would travel such that, see, light can take any path. It can take this path, right? It can take this path. But you know some very important information which says that the shortest distance between 2 points is a straight line. Okay, not so straight. Okay, I missed it. Okay, anyways, but you get the logic. Yeah. So shortest distance between 2 points is a straight line. Hope you remember that. Yeah. Now, here's the thing. Yes. Okay. Looks like a leaf. Okay, thank you. I take that as a compliment, someone. Nice. Okay. Anyways, yeah. Yeah, we'll draw some veins, I guess. Yeah, that works. Nice. Biology class. Welcome to biology. Okay. Now, anyways, so yeah. So the point is, the important point I'm trying to make is that when light goes from A to B, it always takes the path that takes the least amount of time. Okay. Do not forget this. This is very important. Okay. Where is the next slide? Yes. Okay. Now, here's the thing. If you look at it here, light can go from point A here to point B. Let's say if it wants to go, it will go take a straight line like this. It will go in a straight line. Okay. But now observe this, and this, I'll use a laser pointer. If light wants to go to point C, let's say light has gone from A to C, turns out it will never take the straight line. Can anyone tell me why it won't take that straight line, A to C? Why it will never take that straight line? Yeah, Pratyusha, you're right. Yeah, that's right. Fermat's principle. What about others? Yeah, it takes longer time. The issue is it takes longer time. If you think about it, if you go, let's say you go in a straight line, you will see you will have a lot of material of glass to travel, where it travels slower. Yeah, it takes longer time. Turns out the straight line is longer. It takes a longer time. Okay, compared to this path, where you have to make sure you have to adjust and balance such that your time that you take inside the glass is not too much. If you travel straight line, you see this is longer. This line is longer. You will spend more time there. Yeah, because it will spend more time in glass. So you see, light always does this, no matter what. You will observe it everywhere. Okay. Now I have a short question for you guys. This might bum some of you. Okay. So okay, first of all, I have to ask you a question. Do you agree that Fermat's principle works everywhere? Do you guys agree with that? Yes or no? Okay, yes. You guys agree that it will work. So you guys are staunch believers in it now, right? Yeah. Okay. Welcome to my new religion where everybody believes in Fermat's principle. Nice. So here's the thing. Oh, relatively nice, Samant. Okay, fine. You are the guy who will bring down my religion. Okay, anyways. So here's the important thing. Here's a very important thing. I have a question now. If that is the case, if you have 2 points and light always takes the shortest time, then, yeah, Samant, okay, fine. Now, here's the thing. Look at this prism here. This is a prism, right? Okay. I have 2 points marked A and B. Okay. Now you know that light won't take this path because it has a lot of time to travel inside the prism, inside the glass. So it won't take that path. We know that for sure. Okay. So it will take slightly higher path where it gets a lesser amount of, what you say. Yeah, my question is, could light go from B to go to B from A? Then, yeah, the question is, that's the question I'm about to ask. Look, this takes a lot of time. You agree with that? This takes a lot of time. So it takes this upper path. Agree with that? Yes. Okay. Now I'm asking a question. Why couldn't it take this path? This sounds better to me. This is fast. You can avoid the glass completely. How about this? You saw that, right? It could take simply go outside the glass. Why doesn't it do that? Why doesn't it take this path nicely? Or it could even take this path. Maybe this is much more slower because this glass slows down like crazy. If you guys are staunch believers in Fermat's theorem, here you go. Here you have something. What about this? Does anybody have an explanation? Why? There's a chat. Oh, because of the curve. Some are saying because the curved path is not allowed. Hey, Fermat's principle never said curved paths are not allowed. You can go in a curve. That's allowed. Light is not smart as you. Oh, thanks for the compliment. I don't know what to do with that. Okay, nice. Only straight lines. But Nidhi, there was never a rule that in Fermat's principle which said that light has to travel in straight lines. Oh, someone saying light can't bend, but Fermat's principle never says light can't bend. Fermat's principle only says if light has gone from point A to point B, light takes the shortest time. And in fact, I asked this question 2 years ago with a bunch of 10th standard students, and they gave the answer, but it took them half an hour to figure it out. And they were really happy when they figured it out. It was really tricky. Okay. Many are saying light travels in a straight line, but Fermat's principle never said anything about changing that. What do you say? Anything about straight lines? It doesn't say anything like that. It just says if there is point A and point B, light would take the least amount of time. Because there's nothing to change its direction and requires acceleration. Fermat's principle doesn't speak about acceleration. Fermat's principle says nothing. It just says there's only one rule, that is only one rule for my religion, that is light always takes the shortest time if it goes from A to B, if it has gone from A to B. Okay, let's see who has the answer. Because light can't change it unless you say no. Okay, changing direction requires energy. No. It's not only Fermat's principle in question here, right? No, I'm asking Fermat's question. I'm questioning Fermat's principle itself. Turns out it just feels like Fermat's principle does not hold true here. But I would say Fermat's principle is always right. There is a way to solve this problem without using light travels in straight lines, without using it directly. It would take the path of least time. Yes, smallest path is only the straight line. Okay. Samhita, you're very close. Your answer is brilliant. You're very close. Okay. I won't give you the exact answer. Light cannot bend. Okay, you guys are sending me too many answers. Wait. Light cannot bend without passing through. No. Least time from. Okay, former believers. Hi. Wormhole. No, Samant. No way. Speed is constant if it avoids the glass. Yes. Okay, did Fermat prove it? No. Fermat, that's what it's called a principle. Fermat never proved it, Anvita. Okay, so it's just a principle because of that. Okay, what about others? Any explanations? Okay, I'll give you a day's time to think about this. Okay, I'll give you enough and more time. Okay, because it took the students last year half an hour. I gave it at the beginning of the class, not last year, 2 years ago. It took them a lot of time. So does this mean that Fermat's principle is wrong? Does this path mean that Fermat's principle is wrong? I can take this path, right, and be shorter. Samhita's answer is the closest so far, but it's not perfect. Okay, she has to perfect it a little bit. Okay, just saying that much. Okay, figure it out. Okay, can you repeat the question just to be clear? Okay, here's a question. So we know that light won't take this path, the straight line, because it has to travel a lot through glass. There's a lot of medium, glass medium. So it will choose to take this. We know that it will choose to take this path. Okay, if it has gone from A to B, it would have taken this path. Now, I ask a question. To go to A to B, instead of taking this blue path that you see, how about this path below? What about this path? This is better, right? You can simply avoid the glass and stop wasting time at all. It is a better path, right? What if this glass slows down so much, it has very high refractive index, it's very dense, that it takes 1 hour to pass through this glass? I would rather take this path. Yeah, right? So the question is, why doesn't it take that path? Okay, and can you save our religion, the Fermat's principle religion? That's the question. Okay. Okay, some of you have new answers, fresh answers. There'll be no change in speed. Same thing. No. I didn't say anything about speed. Fermat's principle doesn't speak about speed. The only answer, the closest answer is Samita's answer. She has to just reframe it. That's all. There is no change. Same thing to do with diffusion. No. If distance, then time should also increase. Yeah. The thing is, distance increases, but I told you, gave you a whoever said if distance increases, then time should also increase. Here's the issue. Yes, that is true. But then what if this path takes 1 hour? What if light slows down so much that it takes 1 hour to go from this end to that end? I would rather take this path. Yeah, think about it. So that's what I'm saying. Let's say this is our Muralidhar, okay, and this is our Samant, and this is the anaconda, whatever that is, okay, with the Nagin dance and all that stuff. And if you want to save Samant, which path would you take? Would you take, what do you say, through the glass slab or the water, or would you go, what do you say, would you go through the forest, which slows you down like crazy, or would you take this path? That's the question. Would you go around the forest? Oh, Muralidhar and someone, friends forever. Nice. Okay. What's her answer? I can't tell you what her answer is. Okay. I'm just going to give you time till tomorrow. That's right. Okay. You have a day's time to figure it out. Yeah, God save me. Okay, Samant. You're so dead, I guess. Okay. Outside path. Okay. Cool. Yeah, so I think you got this. This is just seems like a loophole in a perfect principle, which always works. Okay, just think about this. I think we'll end it for the day. Get me to this answer, and Satvika is back. Hi. Here's the thing. So just what do you say? Make sure you guys what do you say? Think about this. Get a solution for this, and also some of you can solve that problem which I gave you earlier. Two problems. You can ask Google Uncle. Yes, of course you can ask Google Uncle. You'll get the answers there. But just, okay, somebody asked me to remind the link. What should we write in our notebooks? Yes. So write down the basic principle of reflection, refraction, reflection, and also write down about Fermat's principle, and also write down some problems which I gave you today. Okay, just write them down. I gave you some problems, right? So just try to work them out. Okay, that will be your notes for the day. Scribble a lot. Scribble in the sense neatly write down a solution, a possible solution to the problems. Okay. Can you share the PPT? That won't happen soon. It'll take some time. Okay. I'm sorry that you've missed some slides. It's fine. Next time, please write down. Okay. The PPT will be shared later at the end of all these sessions. Okay. Once this chapter is done, the PPT will be given to you. Okay. Cool. That's about it for the day. I think it's time's up. I can't go longer. Please think about this problem, and please think about the problems which I gave earlier. Okay. This is very important. Just think about it. Okay. So what about the textbook? I do not know about that. I'll get back to you on it. Okay. For now, I think we'll be able to share some portion of the topic. Somebody remembers the link. 1 second. I'll send you the ritku the link, ritku.simulator, whatever that is. It's sent to everyone in the meeting here. There you go. That's the link. Okay. Cool. No DPP or homework for the day. Okay. Nothing for the day. Okay. Cool. The textbook is in Schoology, it seems. That's what I heard. You'll get a break now for 15 minutes, I believe, Anvita. Yeah. Just be back soon. I think your next session is at 5:15, if I'm not wrong. Yeah, I think so. Yeah. Cool. See you guys. See you guys tomorrow. Bye. You can't copy that link. Yes. You can't copy that link. Okay. So bye-bye. I'll see you guys tomorrow. See ya. Bye-bye. Yeah. Okay. That's about it. Wait for another session. No. Yeah, you guys have another session, but I'll be going. Bye-bye. Yeah. See ya. Yeah. Goodbye, guys. Bye-bye. Yeah.